some calculus theorems and about how to use them with critical points. So let's begin with the extreme value theorem. This is kind of one where it's a grass is green type of theorem because it's kind of obvious when you put it into words. So let's say a function is bounded on the closed interval a to b and it's continuous. And there's our function that's closed. Very important. It's a closed interval on both sides. Let's say that's our function f of x. Okay, so the extreme value theorem basically states that as long as these two conditions are met, the function is bounded on a closed interval and the function is continuous, then we know the function must have a maximum and a minimum. That's literally all the extreme value theorem states. Now, it's very important that the boundary is a closed interval. If it was an open interval, let's say we have g of x equals 1 over x, and then we look at it on the open interval 0, comma 1, then our function would look like this, and you can see there's no maximum, and the extreme value theorem here fails because it's on an open interval, not a closed interval. Now, let's look at the intermediate value theorem, IVT here. So that's basically just saying, let's say we have the same function again on a closed interval and the function is continuous. And there's our f of a. There's our f of b. Now basically the intermediate value theorem states that if the function is continuous on this closed interval, then the function obtains every output between f of b and f of a. So like for example, look in this region here, every single function value that is between f of a and f of b, every single y value is reached in this interval, and it applies to the entire function. So basically, if we're saying, let's say f of a is 8 and f of b equals 5, that means there exists a value of c such that f of c is between 5 and 8, and c is in the interval a from a to b. So just, again, every single output of the function between the values at the endpoints is taken into account. And both theorems require a closed interval. That's super important. And that the function be continuous. That's also very important. So now that we know what the theorems are saying, let's look at an example. Let's look at, let's say, h of x equals x cubed minus 3x. And let's try to graph it. Now, you've probably already done a little bit of graphing in algebra 2 or pre-calc, but now we have calculus tools. So that helps a lot. So let me make it a little nicer. 1, 2, -1, -2, 1, 2, 3, 1, -1, -2, -3. Okay, let's say we are looking at this function on the closed interval from -2 to +2. Okay, so first of all, to graph the function, this is a bit of pre-calc or algebra 2 stuff before we get into the calculus stuff. Let's find the roots of this function. Pretty quickly see that the roots of the function are 0 and positive and negative root 3. Now, here's a quick application of the intermediate value theorem. So let's try to compute h of 1. H of 1 equals negative 2, and h of 2 equals positive 2. So now, since this function is continuous on the closed interval between 1 and 2, then we can apply the extreme value theorem. So this h of 1 is negative 2, h of 2 is positive 2. That means between the interval 1 and 2, the function of h must take every single possible value between negative 2 and positive 2. And what we care about for this example here is that the function attains the value of exactly 0. So there is a root between 1 and 2. And it doesn't tell us what the root is. We can use other methods to find that root between 1 and 2 is square root of 3. So now let's go on to some more calculus. Let's try to find something called the critical points of the function. Now, EVT tells us there is a maximum and there is a minimum. However, it says nothing about where the actual minimum or maximum is. Now, critical points will help you narrow down the possibilities of what the maximum and minimum can be for the function. So there are a few critical points that you must check for any function to find its minimum and maximum, and these are the only points where that could possibly be the minimum and maximum. The first one is where the function h of x equals 0, h prime of x equals 0, where the derivative is 0. So you'll see why in a second. Second of all, you're looking at the derivative and you're looking at where it's undefined, because weird things can happen at undefined points. So these are called critical points. And then there's another possibility for the minimum and maximum of the function, and these are the endpoints. However, there's no consistent definition on whether or not we define endpoints as critical points. However, in any case, you still must look at the endpoints to be finding these are always potential minima and maxima of the function. So let's look at the first thing right here. So h prime of x equals 3x squared minus 3, and then we find that where it is 0 is x equals plus or minus 1. So here are the points we have to consider. So we need to consider x equals 1, x equals negative 1. Those might be the extreme values, the minima and maxima. Now, there is no place where h prime of x is undefined, so there's nothing here. And we must check the endpoints. So negative 2 and positive 2. And I'll graph the critical point at x equals negative 1 also. So if we compute h of positive 2 is positive 2, h of 1 is negative 2, h of negative 1 is positive 2, and h of negative 2 is negative 2. So, and these are the points of and positive and negative 1 are where the derivative is 0. So if you take a look at how that looks, if the derivative is 0, that means it's increasing on one side and decreasing on the other. That's the visual way of seeing why where the derivative equals 0 is a critical point. Now, I'll write the rest of our results here. So in this case, it's kind of special because we've tested all of our critical points, and there are two of them that share the highest value. So these are both, they would technically be both absolute maxima, sorry. But at -1, we call this a local maximum because it doesn't look at the whole function, but it is a critical point here. And I don't think you've gone over the rules for finding out whether a critical point is a local maximum or a local minimum, but I'm just going to skip ahead a little bit. We look at the second derivative. H double prime of x equals 6x. And at -1, the second derivative is negative, so we know that it's a maximum. And similarly at +1, the second derivative is positive, so it is a local minimum. So I hope you at least understand how to find the critical points and the points that could be the extrema of the function. Again, check with your teacher to see if endpoints are included in the definition of critical points. But whether they are or not does not change anything. You still have to look at those points to see if they are the maximum or the minimum of the function. If you have any questions, let me know. If you need me to cover anything, I'd be glad to make another video on it. So, and just to remember, these two theorems apply on closed intervals with continuous functions. Alright, see you guys next time.